This conference will
that
now
was
be
the
recorded.
I2C protocol. So we started discussing on this intra-board protocol, which is I2C. So people can call it as I2C, they call it as TWI, they call it as IIC. So different names for the same protocol. So here in case of I2C protocol, the features, if I have to revise the things, first of all, it is a synchronous protocol. That means communication happens with respect to clock. Then another thing is it is a half duplex protocol. That means there is two-way communication, but one can communicate at a given time. And the third thing is another feature of this protocol is this is multi-master multi-slave protocol. So SPI protocol is 20 times faster than I2C protocol, but still people prefer going with I2C. The only reason is in case of I2C protocol, just remember that it has got a feature that is multi-master multi-slave. So we were discussing these things in the previous class, how the inter-integrated circuit protocol works. So we took an example of how a master is communicating with a slave. So we understood wired and concept. And also we saw when is the read operation happening, when is the write operation happening, and there is something called as a condition. So we understood that condition, and we took an example where the microcontroller, our microcontroller wanted to communicate with the RTC. So this was the example we took. So our microcontroller, which is PIC16F877A, wanted to communicate with the RTC for the sake of reading the number of seconds. So how is our microcontroller communicating with the RTC? Is using the I2C protocol. So that we discussed in previous class, the steps which are followed by our microcontroller to communicate with the RTC to know the number of seconds were discussed in the previous class. And along with that, we saw how clock stretching happens when two microcontrollers are communicating, how clock synchronization happens when two masters are communicating. So one is definitely acting as a slave in that case. And we saw what is data arbitration. So if two masters start communicating at the same time, who is going to win the bus? So that is about the data arbitration, and we saw the complete data transfer in the previous class. So today is we are starting with the programming directly. So whatever we discussed here, how our microcontroller wants to communicate with the RTC, so the same thing, whatever steps we have noted down, we are going to achieve this, but we are going to do it as a program right now. So please have patience. This is a lengthier code. Whenever you feel that it is difficult to be understood, so whenever you feel it is quite lengthy at times, please let me know, I can stop. But at least I want to make sure half of the code has been finished in today's classes, so that the rest half I can finish in tomorrow's class. Okay. So to start with, in today's class, as I said, we are going with the programming part. We are going to program this communication which is happening between the PIC16F877A and the RTC. So if you look into this board, here is our PIC microcontroller and here is the RTC. Let me highlight it. So this is the PIC microcontroller, which is PIC16F877A. This is the RTC. Its IC number is DS1307. So now communication should happen between these two chips. Okay, so communication should happen between these two chips. And how is it happening? By using the I2C protocol. Our PIC microcontroller. What? There's a question. Guys, please, your questions, please make sure you're not posting it to the organizers only. I'm being very specific. It is difficult because my logins are, I've got two logins. So if you're giving it to the organizers only the questions, then it is difficult to open the questions every time to answer that. I2C is intra, then how the name is inter-integrated circuit. See, the protocol is intra is that is true, but this is just a name which has been given by the manufacturer, means the company. So the company who introduced this protocol gave the name as inter-integrated protocol, inter-integrated circuits. So in the same board, on the same board, there are two chips, means there are two ICs, and between the two ICs there's a communication happening. So just the name, so there is no specific reason why this name was given. So maybe according to, because the communication happens between the two chips, the name has been given as inter-integrated circuit. Okay, so anyways, let's continue. So we have to make sure the PIC microcontroller has been communicating with the RTC. Guys, remember RTC can communicate using the I2C protocol. Okay, so RTC can communicate with other chips using the I2C protocol. Our PIC microcontroller, if you have known, there is already a UART block. So there is UART protocol support also. So this also has got I2C protocol support. Okay, so the PIC microcontroller also has got the I2C protocol support. So we have to do the initialization of both of these chips. We have to do the initialization of the microcontroller as well as the RTC, which is DS1307. So let us start with this. As I said, there is initialization to be done with respect to the microcontroller, then with respect to the I2C block of the microcontroller, and also the initialization with respect to the RTC. So much work has been there. As I'm saying, it is lengthier, but understanding every function is important. There are several functions, so you have to be understanding one after the other. Okay, so anytime if you have not got anything, please raise your doubts in the chat box to everyone. Okay, all right, so let us start. To start with, let me open the project. I think I have already kept it open. So here is the project. Let me show you where it is actually. So under this I2C, okay, so under this I2C sources, so under this I2C, there's a project by the name DS1307. I have already kept it open. This is the project. So let me open all the files, and also let me tell you what are we actually doing. So here, if you can see, the microcontroller was just reading the seconds from the RTC. Okay, so the example we took in yesterday's class, the microcontroller was just reading the seconds from the RTC. So what we are doing in our project is, our microcontroller is going to read three things from the RTC. One is number of minutes, sorry, first number of seconds, number of minutes, number of hours. Okay, so our microcontroller is going to read three things from the RTC: seconds, minutes, and hours. After that, our microcontroller is displaying that on the CLCD. Okay, so on the CLCD, the time is being displayed in hours colon minutes colon seconds format. Okay, so that is what we are expecting as an output. So if there is any hex file already present, let me try loading it. So please wait, I'm trying to navigate to the hex file if there is any. Okay, so if you can notice, this is what we are going to get. Okay, so let me close and open this PixSimLab again. So RTC has to get refreshed. Okay, so you can see here. So this is what the output is. Okay, I already have got the hex file. I just loaded it. So this is what the output is. Let me repeat what is happening in our project. So the microcontroller is reading hours, minutes, and seconds from the RTC, and that is being displayed on the CLCD. Okay, so this is the project we are doing with the help of the RTC. So let us start with the initialization. So first, if you can look into the main function. So here is the main function, and being in the main function, I'm calling the init config function. So control comes to the initialization. So now under initialization, first I have to initialize the I2C block, which has been present in our microcontroller. Then I have to initialize the RTC, which is DS1307. Then I have to initialize the CLCD because I'm making use of CLCD as well. So to start with, let's start with the initialization of I2C. Okay, so I'm going with the initialization of I2C. So I2C is the block which has been present already. I have to do the initialization of this I2C. So to do that initialization, I'm also passing 100k as an argument. Okay, to the initialization function, that is init I2C, I'm passing 100k as an argument. So why 100k? Remember, this is the baud rate I'm passing. Okay, to the I2C protocol, this is the baud rate I'm passing. And also remember, RTC works with this baud rate. So how did I know? I just referred the data sheet and I got to know that the RTC works with the baud rate of 100k. So to the init I2C function, I'm passing the baud rate, which is 100k. Okay. So now, as usual, every driver code we have been writing in a separate .c file. So initialization or the driver code of the I2C is also being written in a separate .c file, which is I2c.c. Okay, so if you can see here, there are several functions. Okay, so let's see what and all initialization needs to be done. So first and the foremost thing, I am doing the initialization of I2C by passing 100k as an argument. Now tell me, to do the initialization of this I2C, what should I be referring? What should we be referring in order to do the initialization of I2C? Quick guys. Please be responsive. This is really important. Yes. So I have to go look into the data sheet. So here is my data sheet. I have opened the data sheet. Please look into the table of content and tell me which section should I be referring in order to know things with respect to I2C protocol. So which section do you want me to refer in order to do things with respect to I2C protocol? Come on, which section should we be referring? No idea? 10 or 14? First of all, 10, addressable, universal, synchronous, asynchronous receiver and transmitter. It is very clearly saying about UART. So that is where you saw things with respect to UART protocol. And coming to 14, it is special features of CPU. It is not necessary. See here the ninth section, which says master synchronous serial port module. Okay, so this is what we have to be referring, master synchronous serial port. And under that we have got several subsections actually, and I am focused only on the I2C protocol. So you can see here it is the I2C. Okay, so here is the I2C protocol. So this is about the I2C protocol or I2C protocol. So I have to refer section 9.4 from the data sheet in order to know the things related to the I2C protocol. Now read few things here. Okay, so maybe you can read this first paragraph up to this and tell me once you are done. Please let me know once you are done. And only read the selected area. You need not read more than that. Done? Okay. So if I can tell you, the MSSP module in I2C mode. Okay, so this is fully implements all the master and slave functions. Remember, our microcontroller is master capable as well as slave capable. So if you want to treat the microcontroller as a master, you have to configure it as a master. If you want the microcontroller to be treated as a slave, you have to configure it as a slave. So it is master capable as well as slave capable. And if required, it is going to provide interrupts on start and stop bits. Okay, so if it is required, it can provide the interrupt on the start and the stop bits. Also, it says two pins are used for the data transfer. So one is the SCL line, the serial clock line. The other one is the serial data line. So it is being very specific. There are two lines. One is the clock line and the other one is the data line. May I know to which pin of the microcontroller the clock line has been multiplexed with? Clock line has been multiplexed with which pin of the microcontroller? Yes, it is RC3 pin of the microcontroller. The RC3 pin of the microcontroller is where the clock line is being present. So the clock is getting generated. If our microcontroller is being configured as a master, the clock is getting generated at the RC3 pin of our microcontroller. And the data transfer, so it can be receiving the data or transmitting the data, so that is happening at the RC4 pin of our microcontroller. Okay, so the data line has been multiplexed with the RC4 pin of our microcontroller. So now if you refer this section about the registers, it is talking about 6 registers. The I2C protocol is actually having 6 registers. So this first register's name is wrong. Actually, it is SSP con1 register. Okay, so it is SSP con1 register. By mistake, there is just only SSP con return. So remember, there are a total of 6 registers associated with the I2C protocol. So these two are the control registers, SSP con1 and SSP con2. This is the status register. This is the buffer register. This is the shift register, and this is the address register. So we have got 6 registers, 2 control registers, 1 status register, 1 buffer register, one shift register, and the other is the address register. So we have to understand all of these registers one after the other. So according to the data sheet, it says SSP con, SSP con2 and SST stat register are control and status register. So these two are control registers and this is the status register in the I2C mode. And remember, SSP con1 and SSP con2 are readable as well as writable. The two control registers are readable as well as writable. And in case of SSB stat register, means the SSB status register, lower 6 bits are read only, upper 2 bits are readable as well as writable. So lower 6 bits are read only bits and the upper 2 bits are readable as well as writable. Okay, so we will see all of the bits associated to these 3 registers one after the other. And one more core part, it says SSPSR is the shift register which is used to shift the data in and out. Okay, so there are shift registers. Now, just like UART and other protocols, so we have got the shift register here also. That is what you have to be remembering. So every protocol has got a shift register, and by using shift register, what is happening? Data is either coming into the controller or data is going out of the controller. Okay, so data is either coming in or it is going out. Okay, so you can see here with respect to SSP shift register, so data is either coming in or it is going out. Okay, and that is happening with the help of the shift register. Okay, so that is about the shift register, and then SSB buff is the buffer register to which the data bytes are returned to or read from. Okay, so first, usually what happens is, if you have to read the data, okay, remember, if you are supposed to read the data, let's say I am the master. In my master, let's say I have got the I2C protocol, I2C block present, so I2C mode is being present. So what happens, I want to read the data. So whenever I want to read the data, remember, first the data comes into the shift register, and then the data will be shifted to the buffer register, and I will be able to read the data. Okay, so let me have a note done here. So whenever I have to read the data, okay, so first data comes to the shift register. Let's say it is SSP. Yes, sir. So that is the shift register's name. So data first comes to the shift register, then it comes to the buffer register, SSPBUF. Then it comes to the buffer register, then you can read the data from the buffer register. So whenever you have to read, let's say master wants to read, so data from the slave comes to the shift register first, then it is stored in the buffer register. Later I can read the buffer register to know the data. Similarly, if I have to write the data, let's say I am the master, I want to write the data. Means I am the microcontroller, I want to write the data using the I2C protocol. So how am I going to write? I just have to write my data to the SSP buffer register. Okay, so you just write the data to the SSP buffer register. The moment data is being returned to the SSP buffer register, so this is going to shift the data from the buffer register to the shift register. That is SSP SR. Okay, so you just write the data into the buffer register, then data gets automatically shifted to the shift register, and bit by bit the data will be shifted to the slave. Okay, or the microcontroller, bit by bit the data will be transmitted with the help of this shift register. So this is about the transmission. Whenever you are receiving, data first comes to the shift register, then to the buffer register, then you can just read the buffer register. So whenever you are transmitting the data, write it into the buffer register, then the data automatically goes to the shift register, and data will be transmitted by the shift register. So, understood up to this much? Clear up to this? Everybody? Okay. So, next important register is the SSP-ADD, which is the address register. Okay, this is another important register, which is the address register. And this holds the slave device address when the SSP is being configured in slave mode. For example, this all of, oh, sorry. Okay, so all of this I'm talking about, this I2C block is present where? Where is this I2C block present? Come on, where is this block present? Can you tell me in which device, or to with respect to which device are we talking this I2C block? With respect to which device are we talking with about the I2C block? Yes, so this I2C block right now, remember it is being present in our microcontroller. Okay, this I2C block right now is present in our microcontroller. We are configuring the I2C block in our microcontroller. Now, our microcontroller is slave capable as well as master capable. Do you agree that? Do you agree that our microcontroller is slave capable as well as master capable? And if you can notice, when communication happens between a master and a slave, what will the master do in order to pick a particular slave? Don't you think he's going to send the unique address? Don't you think master is going to send the unique address in order to do the communication? Yes. And how will the master know where is the means how will the master know the unique address? For example, let's say there is another microcontroller who wants to communicate with our microcontroller. So our microcontroller should act as a slave. So our microcontroller should have a unique address. And where is that unique address stored? It is in the SSP ADD register. So if you are configuring your microcontroller in the slave mode, how to get the unique address? It is in the SSP ADD register. Okay. Else, if you are configuring your microcontroller in the master mode, okay, when the SSP has been configured in the master mode, remember the lower 7 bits of the address register is the baud rate generated reload value. So the baud rate, in which rate the communication has to happen, the baud rate is stored inside this SSP address register. Okay, so baud rate has to be stored in SSP address register. The lower 7 bits has to be used to store the baud rate of the communication. Okay, if it is in the master mode. So if it is in the slave mode, it has got the unique address. If it is in the master mode, baud rate is being stored in the lower 7 bits of the SSP address register. Okay, so that is about the registers in detail. Okay, so let us see, let us configure one register after the other. Let us understand. So to start with, you want me to explain one more time? Okay, so is reload value referring to the default value? No, so that is not the default value. So remember guys, our microcontroller can be configured as a master, also can be configured as a slave. So if it has to be configured as a slave, then the slave should have a unique address. Okay, every slave should have a unique address. So that unique address is being stored, the device unique address is being stored in the SSP address register. So if you are configuring our microcontroller as a slave, where to get the unique address? You just go read the SSB address register, you will get the unique address. And if you are configuring it as a master, this SSP address register is going to have the baud rate stored inside it. So do you remember when I'm calling I2C function initialization, I pass the baud rate. So that baud rate has to be returned into this SSP address register, not 100K directly. You have to calculate some value corresponding to 100K. So the value has to be returned into the SSP address register. Then 100K baud rate will be generated. Okay, so 7 bits of the SSP address register should be used to store the baud rate. If you are configuring the I2C protocol, the microcontroller in the master mode. Okay, all right. So let's start. So let's start configuring. So initially I have got SSP stat register. So let's configuring. Let's start configuring. So remember we have got 6 registers, 2 control registers, 1 status register, buffer register. There's nothing to configure in buffer register, nothing to worry with respect to the shift register. So I just have to take care of these 4 things. Let me change the color and show you. Okay, so I have to concentrate on this register, this register, this register, and the SSP address register. So let's start with the stat register, status register. It is SSP status register. So if you can notice, the lower 6 bits of the status register are read only. So if it is read only, should we be concentrating? If it is read only, should we be concentrating on this? Should we configure this? No, it is not required if it is read only. So remember, if it is read only, you don't have to be configuring it. Okay, so the next we have got 2 bits which are readable as well as writable. So to start with, first one is the SMP, which stands for sleeve rate control bit. So either in the master mode or in the slave mode, you can have the sleeve rate controlled. So remember, as of now, we are not controlling any sleeve rate. Okay, so right now in our programming, we are not controlling any sleep rate. So let us not concentrate on this. Let us ignore. Let's keep whatever is there as it is. Okay. Also remember, this I2C protocol can also be configured as SM bus. SM bus. Okay, so this can also be configured as SM bus, means system management bus. So if you have to configure the I2C protocol as SM bus, then you have to make use of this CKE bit. Okay, but we are not concentrating on that as well. So please ignore CKE as well. So I am ignoring both of this. I am not controlling the sleeve rate. I am neither configuring it as an SM bus. So both of them I just ignored. The rest six bits, sorry, the rest six bits, if you can see, are read only bits. Okay. So let me just give you a fair idea of what these bits are. First one is the data or address, not of address. So in the master mode, it is been reserved. In the slave mode, it indicates the last byte received or transmitted was a data or was an address. So now tell me, our microcontroller, how are we configuring? Is it as a master, as a slave? How are we configuring our microcontroller? How should we be configuring our microcontroller? Why some of your saving slave? How can you say that it is a slave? Come on. I didn't expect this. Yes, we are configuring it as a master. In our example, communication should happen between the microcontroller and the RTC. Microcontroller is master capable as well as slave capable, but RTC is only slave. So somebody has to be the master, right? And there has to be some device which helps in generation of the clock as well. Remember, we are configuring our microcontroller as a master. Okay, so if you are configuring our microcontroller as a master, should we be concentrating on this? It is a reserved bit. Okay, so do not bother about it. Next bit is the stop bit. Okay, so if you read this P and if it is a 0, that means stop bit is not being detected. If it is a 1, that means stop bit has been detected. Okay, so to know whether the stop bit has been passed or not, you can just read the P value, the bit from the SSP status register. So if it is 0, stop bit has not been received. If it is 1, stop bit is been received. Okay, so then similar to that, there is start bit. If it is 1, you are going to conclude that the start bit has been received. If it is 0, you are going to conclude that the start bit has not been received. Okay, so yes is the start bit. And note this bit is cleared on reset and when the SSPEN is been cleared. So we'll come back to that later. Then another bit is R/W bar. Okay, so this is in the I2C mode only. It is R/W bar bit, and I am configuring in the master mode. Okay, so let me just directly move to the master mode. So this is the bit which is going to tell me whether the transmission is complete or it is in the progress. Okay, so this bit is the one which is going to tell me whether it is in the whether the transmission is been in progress or it has been completed. But please note this note here, ORing this bit with SEN, RSEN, PEN, RCEN and ACKEN will indicate if the MSSP is in the idle mode. So I'm just copying it here. Okay. Okay, so this is the note. Okay, so ORing the this bit in the sense R/W bit. Okay, so it says R/W is being one, transmission is in progress. Okay, so transmission is in progress. Okay, and if it is 0, Okay, if this is 0, transmission is complete. Okay. So if transmission is being in progress, can you tell me what does that indicate? If transmission is still in progress, what does it indicate? The bus has been free or busy? Yes, so bus is being busy. And here, if r slash w is going to give me a 0, this means bus is being idle. Okay, so how to identify that? You have to OR the r slash w bit with SEN, RSEN, PN, RCN and ACKEN. So in that case, if you get a 1, that indicates transmission is been in progress. In turn, bus has been busy. If you're going to get a 0, transmission is been complete. That is, bus is idle. Okay, so that is about the r slash w pin. The next bit is UA, which is update address. Okay, so this particular bit, it is in the slave mode. You can see. So it is used in 10-bit slave mode. So as of now, we are not configuring our microcontroller in the slave mode. So let's ignore. Then coming to the BF, buffer full status bit. Okay, so this is the buffer register status bit. So when you are transmitting, based on this, we will decide if the buffer is being full or not. Okay, so when you are transmitting, let's say you are transmitting the data, and it is 1, it is to indicate that the receive has been complete and the buffer is full. So whether buffer is being full or empty is being judged looking into the BF bit of this status register. Okay, so that is about the SSP status register. Clear with this? And all these 6 bits are read only. You don't have to be worrying with the configuration of this. Clear with the status register? Okay. So let's move ahead. The next we have got is the control register, SSP con1. So first control register. So this control register is readable as well as writable. Okay, so if you can see, all the bits are readable as well as writable. So let us start understanding from the beginning. WCOL is the very first bit, which stands for write collision detect bit. Okay, so that means, can you tell me when is the collision happening? When will the collision happen? Come on, when will the collision happen? So that is when collision detection, the data arbitration we discussed. How is the data arbitration happening? When will the collision happen? Come on, guys. When will the collision happen? When is the data arbitration coming into picture? So collision happens when two masters are communicating. Okay, so remember, when multiple masters start communicating at the same time, it is the collision. So collision detection has to happen, that we do by using the data arbitration. So whoever is having the lowest data is going to win the bus. So collision detection happens when two masters start communicating at the same time. So do you think collision is ever going to happen in our example? In this example, do you think collision will ever happen? No. So ignore this bit also. Okay, so in our case, definitely collision is not happening because there are no two masters communicating. One is a master, one is a slave. So there are no chances of collision. So ignore this bit. Then next is the receive overflow indicator bit. Okay, so this bit is the one which indicates whether the overflow is happening whenever you are receiving. Okay, so when you are transmitting, you don't have to be worrying, but when you are receiving, whether overflow is happening, that means if the data is being continuously flushed to your shift register, then data has been continuously put into the buffer register, then that is the overflow. Okay, so in our case, definitely overflow will also not happen, because every time I'm going to read the data from the seconds register, then I take a break, then I read the data from the minutes register, then the hour register. So in our case, there are no chances of finding means overflow. So let me keep it as it is, how much ever it is. So I'm keeping it as it is. So I'm there is zero initially, so I'm keeping it zero itself. Okay, so that is about the overflow. So then coming to SSPEN, synchronous serial port enable. Okay. So enables the serial port and configures the SD and SCL lines as serial pins. So disables the serial port. Now tell me, should I enable this or disable it? Should I enable the SDA and SCL line to act as serial port pins, or I have to disable it? Yes, remember, I have to enable it. Only then I'm enabling the I2C protocol. So I have to enable, I have to enable the SDA and SCL line. So SCL line is for the clock, SDA line is for the data transmission or reception. So I have to enable both of it. So do not forget to do. That is the very first thing we are doing in the code. See here. I haven't done it. Oh, just a second. So it is SSPEN, which you have to make it a 1. Okay. So let me come here and do it. Yeah, here it is. So SSPEN, I have made a 1. So I have to enable the serial port. I have to enable SCL and SDA line. So I have to write a 1. That is the very first thing we have done. SSPEN is been written a 1. So when enabled, remember SDA and SCL lines must be properly configured as input and output. Okay, so that is up to you. So the next bit is the CKP, so which is serial clock release control bit. Okay, so in the master mode, please see it is unused. Okay, in the master mode, it is being unused. So why do we use this bit is, if you are configuring our microcontroller as a slave, remember there is one concept called as clock stretching. Okay, there is a master who's acting as a slave and he might want to stretch the clock. How will he do that? By making CKP a 0. Okay, so clock stretching is going to be done by using the CKP pin. So as of now, my microcontroller is a master and there is no concept of clock stretching. So that is why in the master mode, this is unused. Next, so the next 3 bits, in fact 4 bits, bit number 3, 2, 1 and 0. So they are used to select the I2C protocol. Okay, so I2C protocol means in which mode, whether it is in the slave mode or it is in the master mode. Now tell me, how do I want to configure our microcontroller? How should I be configuring our microcontroller? Yes, so I have to be configuring it in master mode. Can you look into this and tell me, if I have to configure this in master mode, what should I be writing from SSPM3 to SSPM0? It is 1000. So it is 1000. So basically by default they are zeros itself. Do you think I should rewrite it? These 3 bits, basically they are already 0. Do you think I should be rewriting it? No. So I will just write SSPM3 with 1. Okay. So look at this. Look at the initialization. SSPM3, I have written it with a 1. Okay. So I need not overwrite it again. Only SSPM3, I have made a 1. So rest they are already zeros. I'll keep it zeros. Only SSPM3, I'm making it a 1. Okay. So that is one thing. And one more thing here. See, clock is equal to, there is a formula with which I can tell what value has to be returned into this SSP address register. So let me copy it. It is like this. Okay. Sorry, here. Okay, so clock is nothing but F oscillating frequency divided by 4 multiplied by SSP address plus 1. So using this, I have to write some value into the SSP address register. Now guys, remember, my microcontroller is acting as a master. So inside the SSP address register, what should we be writing? If the microcontroller is acting as a master, what should we be writing into the SSP address register? Come on, what should I be writing? If it is the slave, if my microcontroller is acting as a slave, SSP address register is going to have the unique address. If it is master, what should be written into the SSP address register? If it is master, what should I be writing into the SSP address register? I just said it. Why 1000? Why 1000? So it's baud rate, guys. It's the baud rate. Yes, so I have to write the corresponding value of the baud rate. So I want a baud rate of 100K. Okay, I want a baud rate of 100K. For the baud rate of 100K, there is a corresponding value you should be writing into the SSP address register. And how to find it out? Using this formula. Okay, for the baud rate of 100K, there is corresponding value you should be writing into the SSP address register. You have to find it out using this formula. Okay, so clock is nothing but, you can either refer it as clock or it is the baud rate. Okay, whatever you are passing. So it is the baud rate. So using this, you have to calculate the SSP address register. So how is it? So it is for this thing comes on the left hand side. I'm trying to derive the formula for SSP address register. So this comes here is equal to F oscillating frequency divided by baud. Okay. So this 4 comes to the denominator. So here it is multiplied by 4. Okay. Then it is minus 1. Do you agree with this? Do you agree with this? So SSP address registers, I just derived it. So it is oscillating frequency divided by baud multiplied by 4 minus 1. And the same thing has been written here. See. So I received the baud rate. When I'm calling the I2C function, I pass the baud rate which I collected here. So SSP address register is F oscillating frequency divided by 4 multiplied by the baud minus 1. So just because SSB address is a 8-bit register, to avoid the warning, we have done a typecasting of unsigned character. Okay, so for the baud rate of 100K, the corresponding value has to be returned into the SSP address register, and we are going to write it like this. Okay, so we calculate the baud rate, we calculate the value of the register and write it into the SSP address register. So after this, the required baud rate gets generated for the sake of communication. Understood this? Everybody, is this been clear? And that is about the initialization of I2C. So we are done with the initialization of I2C. Are you people clear? Everybody, can we proceed? So this is about the initialization of I2C. Is this been clear? So there's a maximum of 4 to 5 who responds, but I see good number of participants here. So there are 34 participants. I don't know why everybody doesn't respond. So guys, it takes 2 to 3 seconds of your time to just type a yes or a no. I at least expect that. Okay, anyways, so this much is the initialization and we are good to go. So there are still other registers. So I still have got two more registers. I just finished with two registers. There is SSP contour register, uh, and we finished the SSP address register also. Okay, so con1 we finished, status register we finished, the address register also we finished. So I'm just left with SSP contour register. So I'll come back to the SSP contour register, but that doesn't matter with the initialization. So we'll go with the SSP contour register. So before that, these are the steps I have to be doing in order to do the communication between the master and the slave. Master is our microcontroller, slave is our RTC. So I have to do these steps, I have to follow these steps. So first I have to check if the bus has been idle or not. Second, I have to send the start condition, a start bit, and once the communication is done, we have to send a stop bit also. Okay, and if you want to communicate, continue to communicate, we can also send the repeat start. Okay, now how to start for every small tasks like this. So I'm going to check the bus idle condition for multiple times. I might want to do the communication again and again. So for sending the start bit, for sending the stop bit, for checking if the bus has been idle or not, I have taken some small functions. Okay, so we have written some small functions for that sake. Now, the very first function is to check if the bus is been idle or not. Okay, so I want to check if the bus has been free or it is been busy. So for that, we have written a function by the name I2C wait for idle. Okay, now how to check if the bus has been idle or not? So if you remember, there was a note here. ORing this bit with SEN, RSEN, PEN, RCEN, and ACKEN will indicate if the bus is been idle or not. Okay, so it is something like this. You have to OR R/W bit value with the R/W. So you have to OR R/W with these 5 bits. So SCN, RACN, PEN, RCN, and ACKEN. So you have to OR. Okay. So ORing this bit, remember, if this is giving you a 1, okay, if this is giving you a 1, then that indicates transmission is still being in progress. And if this is going to give me a 0, I am going to tell that the bus is being idle. Okay, so I have to R/W with these 5 bits, and not OR, I would say it like this. I have to OR it with these 5 bits. If I get a 1, transmission has been in progress. If I get a 0, transmission has been complete. And where are these 5 bits? Remember, here. So they are the 5 bits of the SSP contour register. So you notice here, so these are the 5 bits: SEN, RACN, PEN, RCEN, and ACKEN. So these are the 5 lower bits of the SSP contour register. Okay, so out of the 8 bits, the lower 5 bits are with respect to the SSP contour register. So what we have to do is, we need these 5 bits value. Okay, and you have to logical OR with the R/W pin. Okay, you have to get these 5 bits and you have to logically OR with R/W to know if the bus is been idle or not. Now, to fetch this 5 bits, can I directly do something like this? Can I do R/W logical OR with SSP contour? Can I do something like this directly? Do you think I can do it like this? In order to fetch the lower bits, yes. If I go with SSP contour directly, I'm making use of all 8 bits. Okay, but I don't want all 8 bits. I want the lower 5 bits. May I know how to get it? Come on, C programming. So you should be thorough with this. Have to get the lower 5 bits of the SSP contour register. I want the lower 5 bits. These lower 5 bits of SSP contour register. So I have to get 5 bits from LSB. Left shift by 3. Okay, that is possible. So if you are left shifting it by 3, that is also possible. So anyways, to the 3 pins, you are adding a 0. Okay, so that is okay. But apart from that, if I exactly want only these 5 bits, in that case, you are unnecessarily adding zeros. I don't want to add zeros. I want exact 5 bits as it is. So how am I going to get it? Have to get the exact 5 bits. Let me show you here. So let's say SSP contour register has got something like this, and with 0x1f. Okay, let me check if that works. So let's say initially your SSP contour has like something like this: 4, 5, 6, 7, 8. Okay, so initially your SSP contour has this. So I want the lower 4 bits only. The upper 3 bits, let me keep it 0 itself. Okay. So I want this as it is. If it is X, I want it. Whatever it is, I want it to be as it is. Okay. So according to what Prakash says, he is saying and with 0x1f. Let's check if that is possible. Okay, so here I am performing and with 0x1f. So 0x1f will be 0, 0, 0, 1. Then 1, 1, 1, 1, 1. So now do you think this is going to give me this? Yes, so this is correct. So I have to, yes, yes. I don't know how this cursor got like this. Okay, SSP contour and with 0x1f. So this is going to definitely give me, oh, oh, thank you. So and with 0x1f. Okay, so this is how I'm going to get the SSP contour registers lower 5 bits. So that is what we do here in the wait function. So you see here. So I want to check if the bus has been idle or not. So r/w pin logical or with SSB contour and with 0x1f. So if this is 1, remember the transmission is still been in progress. If this is going to give me 0, then the transmission has been completed. Can you tell me, I have made use of a while loop. So when will this while loop gets terminated? When will this while loop gets terminated? So if the condition turns out to be what? The while loop is terminated. Yes. So when the condition turns out to be zero, I'm coming out of the while loop. This literally means I'm waiting till the bus is getting idle. Okay. If there is some transmission happening, I do call I2 wait for idle function. I'm literally waiting until the bus gets idle. Okay. Bus gets free. So that is when this condition turns out to be a zero. So whenever I want to check if the bus has been idle or not, I just call I2C wait for the idle function, and I wait till the bus has been idle. If there is any transmission happening, I wait till the transmission gets completed by using this I2C wait for idle function. Clear? Is this clear? Okay. And whenever I have to start, okay, so whenever I have to do the start condition. So remember, in order to initiate the start condition on the SD and SCL line, I have to just make SEN pin a 1. Okay, whenever I have to do the start condition. So I'm referring master mode for short. So I have to do the start condition. So whenever I want to do the start condition, remember I just have to write SEN with a 1. Okay. So for that, there is a function I have written. It is called as I2C start. Whenever I have to transmit a start bit, I'm going to call I2C start function. So what am I doing here? First, I make sure the bus has been idle or not. Okay, so first I make sure the bus has been idle or not. Then I just make SEN bit a 1. Okay, so that is when I make sure the start condition has been transmitted. So whenever I want to transmit a start condition, I just call I2C start function, where I just make SEN a 1. So that is how you initiate the start condition. Similarly, if it is stop condition, okay, I just have to write PEN with the value 1. Okay, so once it is done, automatically it will be cleared by the hardware. You don't have to be worrying about it. So whenever I have to transmit a stop condition, I just have to write PEN with a 1. So that is another thing I have done here. In the stop condition, I2C stop function, first I check if the bus has been idle or not, and then I make PEN a 1. Okay, so I am transmitting a stop condition. Whenever I want to transmit a stop condition, I just call I2C stop function, and PEN I'll make a 1, which in turn transmits a stop condition. Then if you want, there is repeat start also. Okay, so if you want, in some of the in some of the in some of the cases, if you want to repeat start, means you want to continue the communication, you don't want to stop, you want to repeat start. So let's say I'm done reading the seconds, one set of communication is done, next I want to read the minutes, I have to repeat start it. I don't want to stop the communication, I want to repeat start. So to do the repeat start, I just have to make RSEN a 1. So instead of stopping the communication, you want to do the repeat start, RSEN has to be written a 1. So that is what I do here. Actually, this is not the case. Okay, so it is like this. So first I check if the bus has been idle or not. Then I make sure to do the repeat start by doing RSEN is equal to 1. So when I make this bit a 1, repeat start will be introduced to the protocol. So I'm going to start the communication all over again. So some of the Pixim Lab board, the advanced versions, if you people are using the advanced version of this Pixim Lab board, then it has got this RSEN bit taken. Okay, so you can just make RSEN bit a 1, so repeat start will happen. But if you are using lower versions of Pixim Lab board, there is no option for RSEN. Okay, if you are using lower versions of your Pixim Lab board, there is no option for RSEN. In that case, you have to stop the communication and start the communication again. So you can call I2C stop and I2C start. Okay, so if you are using very lower versions of Pixim Lab board, our simulator, then go with stop and start. If you are using the advanced version, then you can just wait till the bus gets idle and write RSEN1. Understood these three small functions? Whenever you want to check the bus has been idle or not, just call I2C wait for idle function. Whenever you want to transmit a start condition, just call I2C start. Whenever you want to transmit a stop condition, just call I2C stop. And whenever you want to do the repeat start, just call the I2C repeat start function. Understood these small functions? Everybody, is this been clear? And now, I'm talking with respect to the microcontroller only. I'm still with the microcontroller's initialization only. So here, if you can notice, our microcontroller might want to transmit some data at times. See here, it wants to transmit the unique address. It wants to transmit the second register's address. And sometimes it might want to read also. It want to read the second register's value. So remember, whenever our microcontroller wants to transmit, transmitting is nothing but writing. And whenever our microcontroller wants to read, so it is nothing, receiving, it is nothing but reading. Okay. So whenever I want to transmit some data, whenever being a master, my microcontroller being a master wants to transmit a data, I'm going to call a function called I2C write, and whenever I want to receive the data, means I want to read, I'm going to call I2C read function. So the next two functions I'm going to show you is I2C read and I2C write function. Okay. So now let me talk about the read and the write function. Okay. Now, whenever microcontroller wants to write, okay, so it wants to write the unique address first with the intention, then it wants to write the address of the second register. So I hope you know you cannot directly write into the shift register. Whatever data you want to write, you just write it into the buffer register, then data is returned into the shift register, and then the data gets shifted to the slave. Okay, so what happens in the write function? Just see, I check if the bus has been idle or not. I first, whatever I want to write, I accept it here. Okay, let's say I want to write character A, I'm going to accept the character A here. So whenever I want to write, I pass the data what I want to write by calling the I2C write function. So I'm receiving that data. I write that data into the buffer register. Okay, I write that data into the buffer register. So after I write the data, okay, so I write the data into the buffer register, then data will be returned into the shift register, then data gets shifted bit by bit to the slave. And what will the slave do after receiving the data? So let's say here it received the unique address, then it receives the address of the second register. Remember, it is going to give the acknowledgement. Okay, the slave is going to give the acknowledgement. How is it going to give the acknowledgement? You see here. Let me show you. Okay, so here is the acknowledgement. Okay, so this is the bit which is talking about the acknowledgement. Master transmit mode only. So whenever master is transmitting, so this is the bit which is going to tell whether the acknowledgement is been received from the slave or not. Okay, so this is actually in a reverse manner. The slave is ulta. Okay, so whenever acknowledgement has been won, when ACK stat has been won, acknowledgement has not been received from the slave. If ACK stat has been 0, acknowledgement has been received from the slave. Okay, so what is the master doing? He is transmitting. Then after the data has been received by the slave, he is going to give the acknowledgement. So I have to check if I received the acknowledgement or not. And I'm going to look at it by ACK stat bit. So if ACK stat bit has been 1, it is going to tell that the slave has not sent the acknowledgement. And if it is 0, slave has sent the acknowledgement. But I'm so used to say that yes with a 1 and no with a 0. So that is why I'm going to return not of ACK stat. Okay, so ACK stat is going to have 0 if the slave has sent the acknowledgement. So not of 0 is 1, I'm going to return 1. So in my program, when I receive 1, it is understood to me that the slave has uh, given the acknowledgement. Okay, so this is when master is writing. So master has written, it is the duty of the slave to give the acknowledgement. Now let's say master is reading. Okay, so now when the master has been reading, so what it has to do? It has to just read from the buffer register. See here, whenever it is reading, let's say slave is transmitting the data. Whatever slave has transmitted the data first comes to the shift register, then it is in the buffer register. So to know what data it is, just go and read the buffer register. Now, before I read the buffer register, I have to make sure I'm okay to receive the data. Okay, I have to make sure I'm ready to receive the data. And how am I going to do it? By making RCEN a 1. Okay, when RCEN is 1, I'm telling that I'm ready to receive the data you transmit. So when RCN is 0, I'm saying I cannot receive. So master is saying if RCN is 1, he's saying okay, I'm ready to receive. And if RCN is 0, it is telling no, I'm not ready to receive. So what does it do? See here, I want to receive right now. So I make RCEN a 1. And before making RCEN a 1, I'm making sure the bus has been idle. Okay, so I'm checking bus has been idle, then okay, I can receive the data right now. So how to receive? I'm ready. Let me make RCEN a 1. Now this is ready. Okay, next it is checking if the bus has been idle or not, just to make sure slave has transmitted all the data. Okay, just to make sure slave has transmitted all the data, it is checking if the bus has been idle or not. Now it is idle means it is understood that slave has transmitted all the data and it must have been in my buffer register. What am I doing? I'm just reading the buffer register. Okay, so I'm just reading the buffer register. Next thing is, now I'm a master. After I read, is it necessary to give the acknowledgement every time? Is it necessary to give the acknowledgement every time? Come on, if I am reading, I'm the master. See here, let me show it here. So here, I read the address of the I read the data from the second register. Slave transmitted the data and master is done reading. Do you think it is completely necessary for the master to tell that I am done reading? Yes, so master expects an acknowledgement only from the slave. When it is transmitting, it is saying, I'm the master, you're the slave, you have got something I have transmitted, let me know whether you have received it or not. So it is compulsory for the slave to transmit the acknowledgement. But what about the master? I'm the master, so I'm reading the seconds. It is not necessary for me to tell whether I'm done reading or not. Okay, it is up to the master. If the master is an understanding person, he will politely say, I'm done reading. And if the master is an arrogant person, he'll say, why should I be telling you, because I'm a master? Why should I be telling you? So it is that way. So it is up to the master whether he wants to give the acknowledgement or not. But here what we have done is, we are checking whether the slave wants the acknowledgement or not. Okay, if slave wants the acknowledgement, master will give the acknowledgement. If slave doesn't want the acknowledgement, master will not give the acknowledgement. So whenever I'm reading, Okay, I'm receiving the idea from the slave also, whether you want to get the acknowledgement or not. If slave says he wants the acknowledgement, I will make ACK a 1. So ACK here, it is in the receive mode. Okay, so I make a 1. Okay, sorry, it is not acknowledge. Okay, if the user says he doesn't want to acknowledge, then I will not acknowledge. If user wants the acknowledgement, I'm going to give the acknowledgement done. So that is what I have done here. See, I receive. If ACK equal to 1, I'm making 1. That means he doesn't want the acknowledgement. Here, I'm making the acknowledgement. And this last bit, ACKEN, is acknowledgement sequence enable bit. So if you want the sequence of data to be transmitted, then you will say I'm okay with it. So I will do that as well. So ACKEN, I'm making it a 1. And after reading the data, whatever was in the buffer register, I have kept it in a variable called data. I'm going to return the data. So this is about the I2C read function. Clear with the I2C write and read function? Simple. In write function, you write the data into the buffer register and expect an acknowledgement from the slave. In the read function, you read the data from the buffer register, and if you want, you can give the acknowledgement. Else, if you don't want, you don't have to give it. It depends on the user's choice. So this is about the read and write functions of the I2C with respect to the master. Is this being clear? Okay. So now we are done with the initialization with respect to master. So if my microcontroller wants to check the bus idle condition, I'll call this function. If my microcontroller wants to start the communication, I'll call start function, then stop function, then repeat start function. If my master wants to transmit, I'm going to call I2C write function. If master wants to receive, I'm going to call I2C read function. So I'm done with all the things with respect to the master. Now coming to the slave. Okay, coming to the slave, it is very simple. So the slave has already got I2C initialization done. Slave in the sense our RTC. So it has already got the initialization done. There are very few things written. Okay. So that maybe with respect to the slave, let's discuss in tomorrow's class, because if I start it now, I cannot finish it off. So it takes me at least 1 hour to finish off the slave side of configuration. So that is with respect to RTC. That let's do it tomorrow. Some doubt I see. Ma'am, write condition return. You didn't get what this is? Okay, so let me tell you. So you being a master is going to write. Okay, let's say you being the master is writing the data. So whenever you have to write the data, means you want to transmit the data, you cannot write it into the shift register directly. So you have to write it into the buffer register. Then buffer register is going to shift the data into the shift register. So what did I do here? I just wrote my data into the buffer register. Now, after I write the data, the slave there is going to receive the data and he has to give the acknowledgement back. Okay. So after I write, I have to receive the acknowledgement. So how am I going to receive the acknowledgement? By using this, where is it? Okay. So acknowledgement status register. Okay. By using this acknowledgement status register. So I have to make sure whatever I wrote reach the receiver or not. So how will I make sure? I will check the status. I will check whether the acknowledgement is being given by the slave or not. So if acknowledgement is being given by the slave, it is going to have a 0 inside it. And if acknowledgement is not being given by the slave, this bit is going to have a 1. So I'm so used to tell 1 as a true, 0 as a false. Okay. So that is why I'm I'm returning not of ACK stat. Okay, so here when acknowledgement is received, it is saying 0, but when it is received, I'm so used to tell it as 1. So that is why I'm returning not of ACK stat. Got it? So that is about the initialization with respect to the I2C block in our microcontroller. So the rest about the initialization of the RTC and the operations to be performed. So we'll see it in tomorrow's class. Okay. So I hope you people are clear with today's class. Please mark your attendance and then leave the session. So tomorrow is again important. I have to finish the other part uh, of the program. So please do not miss tomorrow's class, and also please make sure you're not joining somewhere in between for the sake of attendance. So because that is really important, guys. You people join in between, you will not be able to take up the things in between. Okay, so it is real. Today's session is already marked. When did I give today's session? Attendance. Okay, anyways. Okay, it is not marked, I guess. All right. So that is it for today. I hope the class has all been clear. If you have got any doubts, please make sure you are asking me up anytime. And please mark your attendance and do not join somewhere in between in tomorrow's class. So please make sure you're joining by 7. I've got only 1 hour of class to finish off this. Okay, so tomorrow again you're not having complete 2 hour session. We'll have a maximum of 1.5 hour session. I'm going to take the class to finish off this I2C protocol. So please make sure you are joining on time, and those who are done marking the attendance can leave the session. Okay, thank you all. We'll meet tomorrow. Those who are done marking the attendance, please quit the session. I'll wait for 5 minutes, and once everybody is done, I'm going to close the session. So thank you all. We'll meet tomorrow.